Hello again. Thanks for studying math with me and watching this video. And I remind you one more time that it's useful to watch these videos with pencil and paper in hand, and feel free to use the controls in YouTube. Today we're going to introduce some additional complexity to the model, and we're going to talk about damping. And damping is defined to be a decrease in the amplitude of an oscillation as a result of energy being drained from the system to overcome frictional or other resistive forces. Now, a good way to think about this perhaps is if you were to immerse the mass into a fluid, and the fluid could even be air and air resistance, that what happens is the fluid pushes back, so it resists the motion of the mass to go down, and if you're trying to pull the mass up, it also resists that motion. So this is a resistive force. Now, in what follows, we're going to assume that the damping is proportional to the velocity, although other assumptions are often encountered, and you will encounter a different assumption in your take-home problem for your final exam this time around. How does this damping affect our fundamental equation? You might remember before we started with MA is equal to minus KX, but now what we're saying is there is a resistive force that is directly proportional to the velocity, so this is a minus beta times dx dt. Now, moving everything to the other side and dividing all the way through by m, we get this expression, which we can call this if we use, as before, omega squared is equal to k over m, and if we call beta over the mass to be 2 lambda. Now, it's kind of a cute mathematical notation as why they do this, but you see, if this is the quadratic operator, d squared plus 2 lambda plus omega squared, then the b squared minus 4ac, the discriminant, becomes 4 lambda squared minus 4 omega squared, and that's equal to 4 times lambda squared minus omega squared. So the discriminant has the same sign, SIGN, as lambda squared minus omega squared, and that is used in some of the notation that goes forward. So this is the equation that we're looking to solve, is this one, and let's look at an example. Now, we are going to be efficient and take the spring and mass system from the first example, but we're going to attach a damper to it that will exert a force of 12 pounds whenever the velocity is 2 feet per second. Then we want to find the displacement at any time t, and we're calling that u of t. So what we really need to do is find the damping coefficient for u prime, and we have the information that allows us to do that. So 12 is equal to beta u prime, and 12 is equal to beta times 2, so beta is equal to 6. So this is the differential equation that we have. If we multiply all the way through by the 2, we end up with this, and we might notice that this is going to be the operator d plus 6 whole squared. So there is going to be a repeated root, a double root, that is going to be negative 6. These are our initial conditions, so this will drive us to get a solution of u of t is equal to minus 1/2 e to the minus 6t minus 2t e to the minus 6t. You should probably verify that you do get that. And this is what the graph of this would look like. And so what happens is we release at this point, and it goes up, but there's so much resistance that it really grinds to a halt pretty much near the equilibrium point. Now, what we will say from a terminology point of view is, since the discriminant was equal to 0 and there was a double root, we say that the system is critically damped, because any slight decrease in the damping force would result in oscillatory motion. And the general solution is going to be this, if m1 and m2 are the roots, or that could be rewritten as e to the minus lambda t, and then this is c1 plus c2 times t, and the graphs of it will tend to look like one of these two things, and the example that we did would have been this bottom kind of curve. So that brings us to kind of the conclusion of this second of the videos that we're going to be watching. I'll see you in the next video.